Okay, good morning to all of you. Uh, so, I think you should be happy that you are in a new course now, huh? And uh, we have to go with quantum mechanics in this course. And, and it's always important that whenever we start quantum mechanics, it's better to remind our past experiences with classical world, right? And we understand that there are many problems in physics that cannot be explained uh, in classical domain. Classical physics fails to explain some of the basic outcomes of the experiments. And the very first example, if I go down, is an example of fine structure of hydrogen atom. Come on. If we go back to Rutherford's model of hydrogen atom, assuming that electron is revolving around the nucleus, and from classical physics point of view, we understand that if a charged particle accelerates, it will produce electromagnetic waves. And if you have an argument that electron is revolving around the nucleus, so you have a nucleus and electron is revolving around the nucleus. Electron has a charge, so if it is revolving around the nucleus, it has acceleration. Because the velocity of the electron changes at every point. So if the velocity of the electron changes at every point, it's accelerating. So if it is accelerating, it should lose energy. And it should continuously lose energy, and finally it should fall into the nucleus. But this is not something that we observe in experiments, right? In experiments, we are able to see there are transitions, there are states. You have the fine structure of hydrogen atom. You have distinct values of energy for electron in different orbits. There is another important problem, that is the theory of alpha decay. Alpha particle, it comes out of the nucleus. And when we measure the energy of this alpha particle, that energy comes out to be 4 mega electron volts, approximately 4 mega electron volts. But the barrier this alpha particle has to cross, this barrier is nearly 24 mega electron volts. So, classical physics tells you that this particle should never pass this wall, because the energy is so high for this alpha particle. Its energy is less than that of the energy of this potential. Its energy is less than that of the energy of this wall. So, classically, this alpha particle should never cross this barrier. But what's the reality? The reality is radioactivity, and we see that there are certain nucleuses which decay. They decay, and these alpha particles come out of the nucleuses, right? And if they come out of the nucleuses, that means the classical physics has no answer to the problem of alpha decay, right? But we can understand these things when we apply quantum mechanics. And quantum mechanics allows us to understand that it is probabilistic for the alpha particle to cross the barrier of 24 mega electron volts, and which is commonly known as quantum mechanical tunneling. So alpha particle can tunnel this barrier. Now, what will be the geometry of that tunneling, we don't know, but it can tunnel. We can predict it mathematically that the alpha particles can cross this potential barrier. Now, so there are the like of many things that cannot be explained by classical physics. So we are going into the domain of quantum mechanics, and the very fundamental equation of classical mechanics is Newton's second law of motion. F is equal to mass times acceleration. And it's a second order differential equation. It's a second order differential equation. I mean, you have F equal to ma. So A is your acceleration. So if I take the one-dimensional thing, it is d2 d2x by dt2. And this F is m d2x by dt2. So we can see that the basic equation that guides the motion of the objects is the Newton's second law of motion. And this Newton's second law of motion is nothing but a second order differential equation, right? And you can predict everything. You can predict the third law of motion and the first law of motion using Newton's second law of motion. So this is the governing equation of classical physics. But when we talk about the quantum physics, you have a basic equation that was given by Erwin Schrödinger, and we call this as Schrödinger's wave equation. So if I write down this Schrödinger's equation, it is IH bar dou by dou t of psi of x and t is H psi of x and t. This is the basic equation of the quantum mechanics that was given by Erwin Schrödinger. And the left-hand side of this equation, you see, is time. It has a single derivative with respect to the time. And the right-hand side of this equation has the Hamiltonian operator. And we know that Hamiltonian operator is minus h cross cal by 2m d2 by dx2, then psi of xt plus v of x psi of x and t. You see the fact that in the right hand side of this equation you have the Hamiltonian operator, and when you write down that Hamiltonian, what you find that you have a double derivative. You have a double derivative with respect to the position. It is d2 by dx2. And the next term is, so this is as we know, it has a link with kinetic energy of the system, and this is our potential energy of the system. Now here we are writing this Hamiltonian operator. We are not writing the Hamiltonian, because Hamiltonian will give us the summation of kinetic energy and potential energy. But here we deal with operators, so we have Hamiltonian operator. So you have kinetic energy operator plus potential energy operator. Now, if you look at this equation, this is an equation. This is not an inequation. This is an equation. And the story that you see in the left-hand side of this equation, it has a single, it has a first order time derivative, right? And the right-hand side of this equation has a double derivative of the position, right? And it has potential energy. If I have, say for example, x plus 10 equal to 15, what is x? X is 5. If I have x plus y equal to 10, what is x? What's y? You need another equation to solve it. So if you have two unknowns, you need two equations. If you have three unknowns, you need three equations. And you can see this crazy looking equation. It has a time dependence on the left hand side, and it has a double derivative on the right hand side. And solving this equation exactly is not possible. And psi, which we have talked about in our previous class, the wave function, right? This psi is the function of x and time. So you have a very complex situation in front of you. You have an equation composing a left-hand side, time dependent, a right-hand side with different symmetry, and the wave function itself is an amalgamation of position and time, right? So what's the way out? What's the way out to get an information from this equation? The way out can be many. Here we will choose a way out in which I use this psi of x and t as the product of two functions. I will choose it as, it's made of what? Position and time. So what's the way out for me for the time being? I can think psi of x and t as, say, g of t. Let me say psi of t and psi of x. Right? Where this psi is exclusively dependent on time and this psi is exclusively, better is to change the notation. Let's use phi here. Let's use phi. So here I will use phi. Okay? So phi is dependent on t and psi is dependent on x exclusively. Okay? Right. So what should I do? I should write down Schrödinger's equation first. Yeah, what's that? That's IH bar of psi of x and t. For Hamiltonian, what I have? Minus h cross square by 2m d2 by dx2 psi of x and t, and then plus v of x, and then psi of x and t. And what we have chosen this psi of x and t is phi of t times psi of x. Right? Now I will take its derivative. I can take it. Right? So what will be d psi of x and t with respect to time, dt? It will be psi of x will act as constant, and for phi of t you will have d phi of t by dt. Right? And should I move on? Okay. And I can take the double derivative of this psi of x and t with respect to dx2. What it will give me? It will give me, what will be constant there? It will be phi of t. So phi of t will be out, and then you will have d2 by dx2 only psi of x. D square. Yeah?
दो बार लेंगे ना इसको बाहर.
What? No, you are wrong. it will come out as one entity, and you will take the double derivative. Okay, so because you don't have to bring it back, then you will differentiate it again. Okay, so you will have phi of t d2 by dx2 psi of x, right? And now I can write down these results in the original equation. What is that? That is I h bar. Yeah. Now you have, come on, psi of xt. It is phi of t out, then d, I think I'm doing it wrong. It is psi of x is out, and then d phi of t divided by dt. The partiality is gone. The partiality is gone, right? And this is equal to, yeah, what will be out? You will have, in this case, what you will have?
Minus h square by 2s.
Minus h bar square by 2n, and phi of t will be out,
D2 phi
and then you will have d2
psi.
psi of x by dt2, then plus v, yeah, this is v of x, then psi of x and phi of t, and phi of t is equal to nothing. They are equal on both sides, right? Now what can I do is I would like to dividing both sides by phi of t and psi of x. Okay? Clear? Come on, when you'll divide, what you'll get? Yeah? You will get I h bar. So phi of t will cancel, and you will have divided by psi of x.
Phi of t. Psi of x will cancel.
Psi of x, yeah, you're right. Psi of x and psi of x will cancel. So you will have phi of t, then you will have d,
Phi upon dt.
d phi of t by dt is equal to minus h bar square by 2m, and what will cancel here? Phi of t, and so we will have psi of x. So psi of x, then you will have d2 by dx2 psi of x alone, and then you will have plus v of x alone here, right?
Yes, sir.
It will be alone. Now, okay. Now you can see that there is some kind of simplicity in this equation. The left-hand side is exclusively dependent on time. And at times, the right-hand side can also have the dependence of time in terms of potential energy, in terms of V of x. But for the time being, we have an equation where we have separated out the time in one side and the independence of time on the other side. Now see, it's an equation, okay, right? It's an equation. But the story in the left-hand side is different, and the story in the right-hand side is different. Now, what is the solution? How should I move on? Because we are doing physics, and when we do physics, we come up with some constants, we come up with some numbers, some constant quantities. But these constant quantities are applicable to our systems, right? Now, this equation can be boiled down only if I say that the left-hand side is equal to something, and that something is equal to the right-hand side. It's like if I say A is equal to B, but B and C is also equal to B. This is the only way that I can think of solving this problem, right? So that way I can do some degree of justice with this equation, right? So here, in this case, what I do is I use E. energy, right? As a number. Energy as a number, right? So I choose E as that constant. So if I do that, I say IH bar by phi of t, d phi of t by dt is equal to, even though I should use En. This is the left hand side, the right hand side will also be equal to E. It will also be equal to E. Clear? Now, this is an equation of importance. This is the basic equation that you have to study when you will continue your course in your next classes as well. And this equation will give us the evolution of time. It will give us time evolution operator. Right? Now let's see how we go on from here. Okay, this is your differential equation. So can we write it like this? This is my IH bar. Then I have d phi of t by dt is E n phi of t. Is it right? I can do that. Okay, so this is d phi of t by dt is minus I by h bar E n phi of t. Right? Okay, now I can write down d phi of t divided by phi of t. I will bring that down. So this is equal to minus I by h bar. Then you will have En and then you will have dt. This equation is itself demanding that it wants to be integrated, right? So you have some starting time and you have the end of that time. So I would like to integrate this equation. Have you finished? So this is my equation, okay? Now, I don't know how to move it. Now, what would I like to do is, I would like to integrate it. I would like to integrate it. That's what I would like to do. And from here, what we will have? We will have, what is in the left hand side? It is integral, I will write it again, it is integral phi of t divided by phi of t. This is integral minus I by h bar En and then what's there dt. So it is from, if my starting time is t naught and the time that ends is t, so what will be the integral of this? It is log of phi of t. So take the limits from t naught to t, from t naught to t. So this will be equal to minus I h bar En is just a number, you remember? Okay, it's just a number, that is En, and then you will have differential and integral will go, so you will have t minus t naught. Right? So this will give us, okay, this will give us log of phi of t minus log of phi of t naught is equal to the same thing, minus I by h bar En t minus t naught. I shouldn't have gone like this. Okay, no problem. I will again come back, okay? So then I will transfer log on the other side. When I will transfer it on the other side, I will have an exponential. So what you will be left with is phi of t by phi of t naught is equal to, yeah? It is equal to e to the power of minus I by h bar En of t minus T naught. Are you feeling something? That you are having a future time and you are having some initial time, and between these two times you have an operator. You have some exponential function. So I can think of this phi of t is phi of t naught times e to the power of minus I by h bar en t minus t naught. So you can correlate this phi of t with phi of t naught. So if this is your past, if this is your present, this will give you the future. This is your present, this will give you the future. When you will operate this present by this operator, it will give you the future. Clear? So this is represented as ut and t naught. And this ut t naught, we call it time evolution operator. Time evolution operator. All right? So if I have to write down, so what have we obtained? We have obtained phi of t is u of t naught phi of t naught. You make an operation on the present, you will go to the future. And it allows you to operate the future and come back to the past. The evolution operator, it allows you. You can, we'll discuss that in some other lecture. So here we have a correlation between present and the future. And you have a time evolution operator. Now what about the other part of this equation? The other part of this equation is what? That is also equal to En, right? So we will see in the next lecture that will lead to the time-independent Schrödinger wave equation. We will discuss that in the next class. Any questions? Come on. No questions? So will you please click it? I will go myself.